Alright, beyond that, there's uh, you could have 10% in the two tails, meaning that you're going to have 5% in the one tail, so 0.05 here, and then to make up 50% you'll have 0.45, so we look up 0.45 in our chart, and 0.45 is here. Alright, it's either 1.64 or 1.65, and again, to be safe, we'll just use 1.65, and that's about it for the areas, the normal types of, or the ordinary types of areas that we'll find in the tail. Alright, so our confidence interval for mu, the true population average, will be a particular sample average plus or minus particular z times the estimated standard deviation of the distribution of x bars. Okay, and again, that doing that problem is very, very simple. So let's look at an example. Again, these problems look the same, and I've done that so that you can see all aspects of an environment. Quality control at a bottling plant routinely takes samples of 50 cans and checks their weight. For the last such sample, the average was 11.95 ounces, standard deviation of 0.37 ounces. Construct the 95% confidence interval for the true weight of cans currently coming off the production line. Alright, so sample data. N is 50. Sample average 11.95 and sample standard deviation 0.37. Okay, there's your sample average. There's sample standard deviation, average, and sample size, and we want a 95% confidence interval. Oops. Alright, so if we got a 95% confidence interval, that means we're going to, on the z, have a situation where we've got 95% in the middle between two symmetric limits, to 5% outside in the two tails, 2.5% in the tail. Alright, so we're looking for a z with 0.025, and we've done that above, and that's 1.96. Okay, so our 95%, well, before we do that, let's calculate S of x bar. S divided by the square root of n. It's the estimated standard deviation of the distribution of x bars. S 0.37 divided by the square root of 50. So it's 0.37 divided by the square root of 50. And for significant places, 0.5233. Okay, so our 95% confidence interval for mu is equal to symbols x bar plus or minus z with 0.25% in one tail times S of x bar, and that's the sample average of 11.95 plus or minus 1.96 standard deviations either way, 1.96 times 0.05233. Alright, so let's calculate that. So we'll have 1.96 times standard deviation, so we'll go up and down that amount, so we'll get 11.95 minus this amount, alright, 11.85, and then 11.96 11.95 plus, alright, the z times the sigma sub x bar is 12.05. So 11.85, 12.05. That's our confidence interval. Alright, and if you want to get some sort of intuition about that, we can say that we are 95% confident that the true average weight of these cans is currently, to reflect the fact that it might change tomorrow, somewhere between 11.85 ounces and 12.05 ounces. Right, somewhere between. We don't know, have no real indication if the 11.85 is good or the 12.05, or anyway. Our best estimate is 11.95, and but it could be anywhere between 11.85 and 12.05. As this production process would like to have their average weight of cans be 12 ounces, this sample information does not contradict or sort of go against the fact that the weight is 12 ounces. Okay, so that's the value of our confidence interval here. Alright, let's look at another problem. Okay, the manager of a fast food restaurant wants to know the average number of customers per hour arriving at a restaurant during lunchtime. Random sample of 30 lunchtime hours yielded an average of 175 customers with a standard deviation of 32 customers. Calculate the 99% confidence interval for the average number of customers arriving per hour during lunchtime. Alright, sample size n. Alright, had 30 lunchtime hours. Average 175, and standard deviation S of 32, and we're asked to calculate the 99% confidence interval for the true average. Alright, the formula for that will be x bar plus or minus the z. Since there's 99% in the middle, there'll be 1% in the tail, and half of 1% is half a percent, or 0.005, times the estimated standard deviation S sub x bar. From the above, we had z with 0.005 at 2.58, I believe. Go up there and check it again if you like. The standard deviation S sub x bar is divided by the square root of n is 32 divided by the square root of 30. Alright, 32 divided by the square root of 30, 5.842. And this is all we need. Alright, so again, so we have this formula here, x bar plus or minus the z, half percent of the tail times S of x bar. So the sample average 175 plus or minus 2.58 times 5.842. So the amount we're going to go up and down, 2.58 times 5.842, going to go 15 up and down. Okay, so it's 175 minus that amount, and for the upper limit 175 plus. Okay, so 159.9 to 190.1. Sorry, 159.9 to 190.1. Alright, so again you can write some sort of statement for that. We are, in this case, 99% confident that the, of course, true average number of customers coming during lunch hour or lunchtime is somewhere between 159.9 and 190.1 customers. Alright, they could use that information to figure out how many waitresses or servers or cooks or whatever they need to do to make this happen. Okay, parking spaces, whatever.